We're going to learn about kinetic molecular theory and specifically how kinetic molecular theory, KMT, applies to gases. Now, kinetic molecular theory does apply to all materials, and some of the things we're going to talk about do apply to solids and liquids as well. But we're going to start with gases because there are some specific ways in which KMT does not apply to the gases when we think of them in terms of real gases. And we'll talk about that at some point, either next week or the week after. So kinetic molecular theory is the idea that the behavior of gases is based on both the particle size and the motion of the particles. And I've broken it down into four specific fundamental things about the kinetic molecular theory. Some books say 5, some books say 3, but they're all included in what I'm going to talk about. So in kinetic molecular theory, one of the most important things is that gas particles are always in constant, rapid, and random motion. And we can see that in the diagram on the right, where these things are moving around. They're far apart, which is another thing about gases we'll talk about in a moment. They're moving all the time and in random directions. And that's one of the reasons why gas particles or gases can expand to fill their container, and why we get some other features that we're going to talk about in a few minutes as well. Beyond that, we're going to assume that the particle size, so the volume of a molecule, not the volume of the sample, not the whole big sample of the gas, but just each individual molecule, is small compared to the distance between the particles. Now, another way of thinking about that is that the volume is essentially 0 for each particle. And we're going to assume now, so that the volume is actually equal to 0. And beyond that, we're also going to assume that they are spherical points. I know that's kind of doesn't really flow, but spherical shape is going to be important. And the volume being A equal to 0 means that we're really thinking of these as being points in space. One of the important things about the distance being large compared to the size of the particles is that the gas particles being far apart, we can get them closer together. And that's why gases are compressible, lots of room in between them. And as the particle gets smaller, as the volume of the container gets smaller, the particles aren't changing size, but the density is going to increase because we're moving things closer together. And even when they get relatively dense, as we can see on the right side, so particles getting closer together, those particles are still far enough apart that in motion, they rarely interact or collide, unlike in a solid or a liquid when they're constantly bumping into each other. Another important thing about gases is that they have no attractive or repulsive forces. Now, we haven't talked about attractive forces as such yet. We will be talking about them in chapter, when we come back to the end of chapter 13. From here, we're actually going to be going to chapter 14. But they neither repel nor attract each other. So there's no intermolecular forces of attraction. And so they behave pretty much like billiard balls. And so on the right here, I have a diagram showing that when one billiard ball hits another, so the cue ball hits the 8 ball now picks up all the energy that the cue ball left behind, and the cue ball stops. And that kind of a collision is called an elastic collision. Oh, I just got ahead of myself a little bit. Elastic collision. We'll come back to that in a moment. Particles do collide with each other, not as often as in liquids and solids, as I said, but they do collide with each other. And they also collide with the walls of the container. And it's those collisions with the walls of the container that you recall that gives us pressure. When they collide, as I said, the collisions are perfectly elastic. And that's just a fancy way of saying that there's no loss of Ke is kinetic energy. And as you'll see in a moment, that's very important because kinetic energy is important to the concept of how gases move. Finally, let's get to kinetic energy. The temperature of a system, and this applies for solids and liquids as well, the temperature of a system measures the average kinetic energy of the sample. And if you recall, when we were watching the gases FET the other day, I was pointing out to you that while the particles all move at different speeds, there's an overall average. And it's this temperature that measures the overall average. I'm going to put a big star on this one because this is one we're going to keep coming back to in this unit. We'll come back to it in the next unit. We'll come back to it in the following unit. And this is a question which I ask in every unit on every test. And I want to make sure that we put a big star on that so everybody remembers and notices. Kinetic energy, the average kinetic energy of a sample is what the temperature is. Now, what is kinetic energy? Kinetic energy is energy due to motion. So when particles are moving, when you're moving, you have kinetic energy. And so the kinetic energy is defined as this equation, 1/2 the mass of the particle times the velocity or speed of the particle squared. And on the right, I have a diagram which shows how the velocity of helium atoms changes with the function of temperature. And this is a direct relationship because kinetic energy measures temperature, and this is the average kinetic energy. The average kinetic energy. This equation up here, the kinetic energy, this can be for a particle or for the average. So it can be either for a particular particle if you're looking at the velocity of just that particle, or if we talk about the average velocity, which is what we're seeing on the right, the average velocity of the helium atoms. So there it is, average velocity of the helium atoms. As the temperature goes up, the kinetic energy goes up, and the average velocity or the average speed also goes up. And just to give you an idea, helium atoms are so light, and 300 Kelvin is about room temperature. At 300 Kelvin, the speed of helium atoms is about 1,400 meters per second. If we go through our conversion factors, I'm not going to make you do that for this one, we get this to about 3,200, are you ready for it, miles per hour. That's some moving molecules. Those guys are moving really, really fast. And we'll talk about how that affects things in a few minutes. And there's going to be a video that you're going to watch that's going to explain how helium actually makes your voice go squeaky. So those are the four main basics of kinetic molecular theory. And on the homework, I'm going to ask you to re-explain those, hopefully as much as possible in your own words. Now, there are two behaviors of gases that are related to this kinetic molecular theory, related to how the gas particles move. And the first one is one you may be familiar with. It's called diffusion. Diffusion is when one material moves through another. And you've seen this probably in biology when we have diffusion through cell walls. In terms of gases, the example that I like to think about is aromas from cooking. And in these aromas from cooking, we can kind of get a sense for how kinetic molecular theory works. If you think about it, what moves through your home faster? What gets up to your room faster? When somebody takes a pint of ice cream out of the freezer, or when somebody's baking cookies in the oven? And why should that be? Well, remember, diffusion, gas particles, the speed is based on how light the molecules are, or how high the temperature is. And so at higher temperature, the diffusion is faster, and so gas molecules coming off the cookies baking in the oven are going to move a lot faster, and they're going to make their way through your house a lot faster than that cold ice cream, the particles coming off the cold ice cream. Now, diffusion is a kind of difficult process to model, because as you can see below, and diffusion is down here, we have these two particles intermixing, and they're going to bump into each other, and they're not going to always move in a straight line. Oh, and by the way, if you notice that the heavier molecules on the left and the lighter molecules on the right, that when we look at how fast they're moving, these lighter molecules are moving faster through the heavier ones, and so they get faster into the heavier molecules. And we're going to see an example of that and a demonstration on the next page. Related to diffusion is something called effusion. So EFF, effusion. And effusion is on the right. Its definition is the escape of a gas through a pinhole into a vacuum. V-A-C-U-U-M. Let's try to get to spell vacuum correctly. To be precise, it does have to be into a vacuum, but doesn't always work exactly that way. The nice thing about it, if you can see below, so when those gas molecules are moving into that vacuum, there's nothing to interfere with them. And this rapid random motion is important because some of the gas molecules, like this guy, is going to hit the wall and bounce back. So you have to have a molecule, some of these molecules have to have exactly the right speed and exactly the right direction to get through that pinhole. So it doesn't happen all at once, but it does depend on two things. It depends on temperature. So as the temperature goes up, they get faster. And it also depends on the mass of the molecules. If we assume we have a sample that's completely all one molecule or all one atom, then the molar mass is what we're really looking at, or the atomic mass. And so as the atomic mass is going up, if we go back up to that equation, we will see that the speed, I didn't want that, that the speed of the molecules goes down. The faster you are, the heavier you are, the harder it is to go fast, and so molecules are going to move slower. I'm going to show you a little bit more about that on the back. I've got a little diagram to show you. So this effusion can be used. I'm not going to make you do any calculations with it, but you could, to study both the rates of the gases moving, so how fast are those gases escaping, and we can also use it to compare gases with different masses. And yes, one is spelled with a single S in the middle, and one is spelled with two S's. The example that I like to give for this is helium escaping from a latex balloon. Why a latex balloon? Because latex balloons have lots of pores. They're porous. Although you can't see it on the molecular level, on the atomic level, the latex balloons are porous, and so those helium molecules, helium atoms, because they're very small and because they're moving very fast, can escape. And most of us have experienced that poor old helium balloon that you bring it home from the fair, and then by the next morning, the latex balloons anyway, the helium balloon has shriveled up and is hovering somewhere near the floor. This doesn't happen with the mylar balloons because mylar balloons are not as porous. The holes between the pieces of mylar are smaller, so the helium doesn't effuse as quickly. Okay, let's turn the page over and talk about the factors that affect these rates. And I've already given you a few. Oh, I didn't get rid of that. Let me get rid of that underlining there. Sorry about that. I thought I had done this ahead of time. That's all right. Just like being in class. So the rate of the particles depends on the rate of gases diffusing, and diffusing depends on the velocity of the particles. And if you take the kinetic energy equation on the back, on the front, and you rearrange it, you get an equation that tells you that the velocity of the particles is equal to square root. Under the square root, we're going to have the kinetic energy, and in the denominator, 2 times the kinetic energy, and in the denominator, we're going to have the mass of the gas. So the velocity of the gas goes up as the temperature goes up because the kinetic energy is going up. And so we saw that on the previous page. But now we can also see that the rate is indirectly or inversely proportional to the mass. And again, since we're looking at the mass of of all one sample, the mass that we're looking at is really the molecular mass. And as you can see from the equation up above, since the square root of the molar mass is in the denominator, as it goes up, that means that the velocity has to go down at the same temperature. And another important thing, all gases at the same temperature have the same average kinetic energy. So when we compare gases, we're comparing kinetic energies. The average kinetic energy is the same at the same temperature, and that's important. But what's changing now is the mass of the gas and the speed of the gas. And so on the right here, I have the molecular masses, and this one says 1,960 meters per second. I'm not sure why that's different from, that's hydrogen, not helium. There's the 1360, about 1,400 for helium. Helium is twice as heavy as hydrogen gas. And then as you move up, water gets smaller and smaller. And so we have kind of this almost an exponential decay kind of curve that as you get heavier and heavier, you get slower and slower. In order to demonstrate this in a practical way, I'm going to show you a video. So at this point, let me just explain what's going to go on here, and then you're going to stop the video. Stop this video and go and watch the diffusion and ammonium chloride video, which is going to be the second video that I've got attached to your Google information. So what's going on here is that hydrogen chloride, it's hydrogen chloride as a gas because it's not aqueous. If it was aqueous, it would be hydrochloric acid. And ammonia, NH3, as a gas, when they come together, they react to form ammonium chloride, which becomes a solid. So they're going to make ammonium chloride, but where they make ammonium chloride is going to depend on where they meet, and where they meet is going to depend on how fast they move. So go and watch that video now, and when you're back, we will be able to talk about what's going on. So I've assumed you've watched the video. If not, please go watch it. And here's the results of our experiment. when the hydrogen chloride and the ammonia met, they met somewhere around here. And they formed a ring of that white ammonium chloride right about here. Now the ring was a little diffuse, right? It didn't stop at one place, but it did look like it was more towards one end than the other. And so this is our ammonium chloride. Right here. So it shows that we are actually meeting closer to the hydrogen chloride than to the ammonia. And this should make sense because the ammonia has a mass of about 17.0 AMU. That's for each molecule. And the hydrogen chloride, each molecule is about 36.5 AMU. And because of that, the lighter ammonia moves faster. And in fact, it moves about 1.5 times faster. So it moves 1.5 times the distance that the HCl moves, and they meet not in the middle, but they meet closer to the heavier one. So they meet closer to the heavier gas. For the next two videos, we're first going to see a video from one of my favorite British groups called the Naked Scientists. As they say, it's stripping down science. It's the science that's naked, not the scientists. And they're going to explain that because helium has a mass 7 times less than air, it has a speed which is going to be a lot faster. So the speed of the helium must be higher. This is going to affect your voice, but not necessarily the way you think it affects your voice. And so the video is going to explain how helium makes your voice get higher. After you watch that video, we're going to watch something, a video about sulfur hexafluoride, which some people call anti-helium in this respect. Sulfur hexafluoride is a molecule that has the sulfur in the middle. We've never seen six atoms around before. This is a more advanced topic, but the fluorines, so the sulfur is in the middle, and the 6 fluorines surround the sulfur like so. And it's actually a relatively inert molecule, but if you look at the size of the tank that they're using, that small tank that they use cost about $150. And so it's a very difficult gas to get a hold of. It's a special gas used in processing semiconductors. It's the opposite of helium because now it's 6 times more massive and 6 times denser than air. It's about 146 grams per mole. So its average speed is lower and its frequencies are lower. So the resonant frequencies that they talked about in the previous video, those resonant frequency are much lower, and so your voice goes down. And the other thing that's cool about it, as they do at the end of the video, is it's an invisible gas, but you can float a boat of a fairly light boat made of aluminum on it. And that light boat contains air, and as they scooped the SF6 into the boat then, just like a boat full of water, capsized and sank. So that does it for us with kinetic molecular theory. The homework will come on Friday, and that will be due on Monday. For tonight, if you're watching this on Thursday, March 19th, the homework for tonight, get that aspirin lab done. All right. Have a good weekend, and I will be back with more videos. We'll be back with more videos next week.